Continuity on a closed interval. Hello everyone. To begin today's lesson, let's first look back at what we have already covered. In our previous sections, we focused primarily on continuity at a single point, essentially learning how to verify if a function is unbroken at one specific value of x. However, as we move into more practical applications of mathematics and physics, we find that analyzing a single point is often not enough. In these fields, we frequently need to determine if a function remains continuous over an entire specific range of values, rather than just at one spot. This leads us to our current topic, the concept of continuity on a closed interval, which is mathematically denoted as the closed interval from a to b in the upcoming slides. We will define exactly what this interval entails and the specific conditions required to ensure a function is continuous from the start point, all the way to the end point, b. Understanding the concept. Now that we have established the need to move beyond continuity at a single point, let us dive deeper into the concept of a closed interval. First, let's define our terms. A closed interval, denoted as a to be in square brackets, includes all real numbers x such that x is greater than or equal to a and less than or equal to b essentially. This means the endpoints a and b are included in the set. For a function f of x to be continuous on this interval, it must be unbroken throughout the entire stretch from a to b in practical terms. This means there are no holes, jumps, or vertical asymptotes from the start to the finish, including the boundaries themselves. It is important to remember that for this specific analysis, the function is only defined within the boundaries of a and b. We are not concerned with what happens outside of this range. Because the function is restricted to this interval, we encounter a unique situation with limits. At the endpoints, we cannot check the limit from both sides because the function does not exist outside the interval. Therefore, at the left endpoint a, we can only approach from the right, and at the right endpoint b, we can only approach from the left. In the next slide, we will translate these conceptual ideas into the three specific mathematical criteria you need to prove continuity on a closed interval. Criteria for continuity on a, b dollar. Now that we have a conceptual understanding of what a closed interval is, let us examine the formal criteria required for a function to be considered continuous over that range. For a function f to be continuous on the closed interval from a to b, it must satisfy three specific conditions. First, we must verify continuity on the open interval. This means the function must be continuous at every single point strictly between a and b. In formal terms, for every value c where c is greater than a and less than b, the limit of f of x as x approaches c must be equal to the function value f of c. This is the standard definition of continuity we have used previously for single points. Second, we must check the continuity at the left endpoint. As we discussed in the previous slide, the function is not defined for any values less than a. Therefore, it is impossible to check a two-sided limit. Instead, we only consider the right-hand limit. We conclude that the function is continuous at a if the limit of f of x as x approaches a from the right is equal to the function value f of a. Third, we apply the same logic to the right endpoint. b. Since the function is not defined for any values greater than b, we only need to consider the left-hand limit. The function is continuous at b if the limit of f of x as x approaches b from the left is equal to the function value f of b. In summary, a function is only continuous on the closed interval from a to b if it passes all three of these tests. To help you visualize these requirements, I will use a real-world analogy in the next slide. Real-world analogy. Now, to help you visualize the three technical conditions we just discussed in the previous slide, let's use a real-world analogy. Imagine you are walking along a hiking trail that begins at milestone A and ends at milestone B. In this scenario, for the trail to be considered continuous, there should be no gaps, broken bridges, or sudden jumps in the path as you travel between milestone A and milestone B. This represents the first condition we mentioned, continuity on the open interval. Now, let's consider the start of your journey. At milestone A, you cannot approach the starting point from behind because the trail does not exist before that point. You can only move forward into the trail. This is exactly like the right-hand limit we discussed in Step 2. We simply ensure the path begins smoothly as you move forward to the right. Similarly, when you reach the end of the trail at milestone B, you are arriving from the left. You cannot approach the finish line from the other side. Therefore, the trail is continuous at the end if it leads you smoothly into the finish point from the left, which corresponds to the left-hand limit we defined in Step 3. By keeping this analogy in mind, the mathematical requirements for a closed interval become much more intuitive. Now that we have a conceptual understanding, let's move on to the next slide and apply these steps to a concrete mathematical example. Illustrative example. Now that we have established the theoretical criteria and the hiking trail analogy, let us apply those concepts to a concrete example to see how this works in practice. Please look at the function f of x equals x squared plus 2, which we are examining over the closed interval from 1 to 3. To determine if this function is continuous on this interval, we must systematically apply the 3 steps we discussed in the previous slide. Step 1 is to check the open interval, which consists of all values between 1 and 3. We can observe that f of x equals x squared plus 2 is a polynomial function. As we know from our previous studies, polynomial functions are continuous for all real numbers. Therefore, it follows that the function is continuous for every value of x within the open interval from 1 to 3. Step 2 requires us to verify continuity at the left endpoint, where x equals 1. First, we calculate the function value. F of 1 is 1 squared plus 2, which equals 3. Next, remembering that we can only approach this boundary from the right, we find the right-hand limit. The limit of x squared plus 2 as x approaches 1 from the right is also 3. Because the right-hand limit is equal to the function value, the function is continuous at the left endpoint. Step 3 is to check the right endpoint, where x equals 3. First, we find the function value. F of 3 is 3 squared plus 2, which equals 11. Then, we calculate the limit as x approaches 3 from the left. This limit also results in 11. Since the left-hand limit equals the function value, the function is continuous at the right endpoint. In conclusion, because all 3 conditions have been satisfied, the interior of the interval, the left boundary, and the right boundary, we can formally state that the function f of x equals x squared plus 2 is continuous on the closed interval from 1 to 3. As we move forward, keep in mind how we specifically used one-sided limits for the endpoints. This is a critical detail that we will elaborate on in the next slide to help you avoid common pitfalls. Common mistakes to avoid. Now that we have walked through a practical example, let's discuss some common pitfalls to ensure you don't make these mistakes in your assignments or exams. First, be very careful about using two-sided limits at the endpoints. You should not attempt to calculate the general limit of f of x as x approaches a, as we discussed in the earlier slides. The function is only defined within the boundaries of the interval. Therefore, you must use one-sided limits, specifically the right-hand limit for the left endpoint and the left-hand limit for the right endpoint. Second, avoid the mistake of ignoring the endpoints entirely. It is common for students to verify that a function is continuous within the open interval, from a to b, and assume the work is finished. However, for a closed interval, you must explicitly verify the continuity at both the starting and ending points to be certain. Finally, do not confuse open intervals with closed intervals. It is important to remember that continuity on the open interval, from a to b, does not automatically guarantee continuity on the closed interval, from a to b inclusive. The two are different requirements, and the closed interval is more restrictive because it includes those boundary points. Keep these points in mind as we move toward our final summary of the topic. Key takeaways. To wrap up our lesson, let's review the key takeaways to ensure you have a solid grasp of continuity on a closed interval. First, remember that a closed interval, written as a to be in square brackets, is inclusive, meaning it specifically includes the endpoints A and B. Second, regarding internal continuity, the function must be continuous at every single point C within the open interval from A to B as we saw in our example. This means there are no gaps or jumps in the middle of the range. Third, we have the left endpoint condition. Because the function isn't defined to the left of A, we only care that the limit of f of x as x approaches A from the right is equal to the function value at A. Fourth, we apply the same logic to the right endpoint. The limit of f of x as x approaches B from the left must be equal to the function value at B. Finally, keep in mind the overall requirement. All three of these conditions, the internal continuity and both endpoint conditions, must be satisfied. If any one of these fails, the function is not continuous on the closed interval.